Hello, today we're going to be talking about types of functions. And we're going to be talking about types of functions because once you have a basic grasp of what a function is, it can be really helpful to gain some exposure to some of the common types of functions that you can expect to see. So I've listed some of these over here on the right in the outline, and we are going to be covering the algebraic and graphical representation of each of them briefly. So starting off with lines, a line has the equation f of x is equal to mx plus b, where m is the slope and b is the vertical or y-intercept. I'll write y-int for short. And a line has a base graph that, unsurprisingly, looks like a line. And this line may appear differently depending on the values of m and b. The value of m, or the slope, exactly like it sounds, controls the steepness of this line. So if m were higher than it is in this base graph here, then the line would appear more steep. And if m was lower, then the line would be less steep. However, if m is negative, then you would have a line that runs from the top left to the bottom right instead of the bottom left to the top right. So if m was negative, then you would have a line that looks something like this. And the value of the vertical intercept, exactly how it sounds, controls at what point this line crosses the vertical axes. And that should cover enough to get you started with lines. Moving on to quadratics, lines and quadratics are actually members of the same family of functions, but they're seen so often that we distinguish and give them their own special names. We'll cover that more when we talk about higher order polynomials. For now, quadratics, or quads for short, have the equation f of x is equal to ax squared plus bx plus c. This is referred to as standard form for a quadratic. You might see it differently depending on if it's factored or if it's in intercept form. Yeah, so at this point we have a, b, and c, and each of these are constants. And you have this theme in equations of this form where c is the vertical displacement of this graph, or of this equation. And because if x is equal to 0, this is 0, this is 0, it actually turns out to be the vertical intercept of our function. So this quadratic, the base form of a quadratic, looks something like this, where this would be touching the horizontal axis. You have f of x and x. And yeah, so this is the base form. In this form, it has one intercept, call it, at 0. It would actually be a double intercept, but it's besides the point. You might also see a quadratic, if it's been shifted, have kind of a form like this. And what this means is that in order to find these two x-intercepts, also referred to as roots or zeros, you would have to factor this equation up here. And if you're not sure how to factor, drop a comment down below, and if there's enough demand, I'll make a video on it. And this should be enough to get you started on quadratics. If you have any more questions, like I said, drop me a comment below. I'll try and answer them or make a video to address them. And the reason that I'm kind of glazing over this is because, like I said, lines and quadratics are members of a larger family of function known as polynomial. And a polynomial is a function that has an equation that is a mixture of constants and powers of x. So what that would look like if we have a polynomial, we'll say introduce some language here of degree n, where n is some constant. We're going to represent each of our constants as a and then a subscript to distinguish between them. We have f of x is equal to an, x to the power of n, plus a of n minus 1, x to the power of n minus 1. And then there will be some more terms in here. And on the other side, we'll have a1 multiplied by x plus a0. And this is super general. It depends really on what your value of n is. But if we just take a moment and assume that n is equal to 2, then we would see that what we have is our quadratic. Similarly, if we let n equal 1, then we would have a line. So people are often interested in the properties of polynomials because they encompass so many different functions that we see in everyday life. And in fact, a lot of the times, more complex functions we will expand or represent using a series of polynomials. We'll approximate them because polynomials are typically just so nice to work with, as we'll see later. Anyways, for right now, maybe we'll just draw the graph of a couple of other values of n. So if n were equal to 3, then instead of our base quadratic that kind of looks like a smiley face, we would have maybe like an awkward smiley face. You know, it's not sure if it's smiling. And yeah, you notice on one side it goes down and to the left, the other side on the extreme it goes up and to the right. And if we had an even value of n, say n equal to 4, then you might have something like this. So kind of the embarrassed smile maybe. And here, both extremes will head off in the same direction. And the reason that I just chose to show that really quickly is because this is a characteristic that's shown in all degrees of polynomial. So if you have an odd degree, you'll always have one extreme going one way and the other extreme going the other way. But if you have an even degree of polynomial, you'll have both extremes going the same way. And moving on to exponentials, if you've ever been interested in the spread of disease or population growth, they use this in chemistry sometimes. Also commonly used in finance. That's when it comes up a lot, when you have an interest rate and you have something growing by a constant percentage. Oftentimes you'll get an exponential. But if we look at the equation of an exponential, what we have in the base form is f of x is equal to b to the power of x. And this will have a base graph of, what's happened there? We will have a base graph that kind of looks like this. And this might look familiar to you, might not. Okay, either way. And this typically crosses in the base form at 1. And the reason that is because if x is equal to 0, then b to the power of 0, no matter what b is just some constant, remember, it's some number. B to the power of x is 1, because b to the power of 0 is 1. And for this shape actually corresponds to specific values of b. Namely, if b is greater than 1, then you'll have this growth, right? Because if b is greater than 1, say b is 2, then you would have 2 to the power of something is always going to be greater than 2. Conversely, if b was, say, less than 1, then you wouldn't have this exponential growth. Instead, what you would have is this exponential decay. It's called similarly crosses at 1. And this is for b is greater than 0, but less than 1. And of course, if b is equal to 1, then it would just be a straight horizontal line, because 1 to the power of anything is 1. Anyways, not to get too far away from exponential decay, this graph decays because if b is less than 1, say b is 0.5, then 0.5 times 0.5 times 0.5, no matter how many times you do it, it's always going to be less than 0.5, right? It's less than 1, so it will decay, and there will be some leveling off point here where you'll notice little decay for large increases of x. But anyways, that should give you a basic idea of the shape and characteristics of an exponential. And next we're going to talk about actually the inverse of an exponential, called the logarithm. And the logarithm is kind of tough for a lot of people to get a grasp on at first, because it's the inverse of an exponential isn't a concept that it's not readily apparent to everybody. It's not as easy as, say, taking 1 over some number to be the inverse, for example. So a logarithm, the notation for a logarithm, you would have f of x is equal to log base a of x. And I'm not going to do a full introduction to logarithms. If you want to see more about logarithms, the properties of logarithms, drop a comment. I'll make a video for it. But for now, just know that we have f of x is equal to log base a of x. And this graph has a form of something kind of like this, where it starts really low, increases very, very fast, and will level off. And this will be 1. And just for a moment, if we have the graph of an exponential, we would notice that this is the mirror image of this exponential, like the exponential that this logarithm would correspond to, for example. That's what we mean when we say that it is the inverse of an exponential. Anyways, not going to go too in depth into logarithms. I want to have some time to talk about the different kinds of trigonometric functions. And trig functions come from properties of right-angled triangles. So I'll write trig functions for short. And there are 3 main types of trig functions that you will see. One of them is just a ratio of the other. So you have f of x is equal to sine x, or f of x is equal to cosine of x, or f of x is equal to tangent or tan of x. And tan of x is just equal to sine of x over cos of x. So really, if you're just new to this and you're trying to understand, the bulk of your time should really be used understanding sine and cosine, which form this more complicated tangent function. But we're just going to sketch each of their plots really quickly. So say that we have 2 pi here, minus 2 pi there, f of x, and x. For sine, you would have, something like this, roughly. Not to scale, obviously. So you would have 1 and minus 1. And the interesting thing is that cosine is actually just a shifted form of sine. So if we were to shift sine by pi by 2, pi over 2 to the left, then we would get cosine. So if we have 2 pi on one side minus 2 pi on the other side, then cosine would look something like this. Great. And both of these functions are bounded. That is, they don't go above or below plus or minus 1 in their base form. And they also repeat forever. A characteristic of these trigonometric functions is that they're periodic, which means that the ratio of them is also periodic. So if we plot tangent, this looks kind of crazy if you first see it, because it's the ratio. So it will go to infinity or negative infinity when cosine of x goes to 0. So it looks kind of something like this, except you would have repeats of it. Right. And if you're unfamiliar with trigonometric functions and how they work and kind of where they come from, then you can check out some of our other videos on them. We have some talking about how trigonometric functions relate to right angle triangles and some of the properties of trigonometric functions. So if you're interested in learning more about functions or just calculus in general, or more about engineering, then head on over to the Engine Learning channel and subscribe. As always, thanks for watching. If you learned something new, let me know by leaving a comment below.